So we are looking at intermolecular forces. You have this graph on your paper. I want you to talk to your seat buddy or somebody near you if you don't have a seat buddy and see what you find strange about the trends on this graph. Go.
Closest one to zero is group DIA. But the heavier they are,
All right, what do you think is weird on here? They start going back up around 30. But what is weird about the trends of it? So that's something that they have in common. What's strange?
they all go down,
But do they all go down? No. So there's something strange about this guy versus these three, yes? Okay. And that's what our discussion of IMFs is going to take us through. That's what we're going to talk about, is why that is. And I'm going to circle back to this graph at the very end. I'm going to circle back to it at the end of today, and then I'm going to circle back to it at the end of tomorrow as well. So everything's going to come back to this graph. All right? So let's talk about some terminology first. So we have stuff called intramolecular forces. Intra means between or within. Okay? So you can almost think of it as within. So for example, we have something called an intranet. And I'm going to do a okay job of explaining that. If I explain it to my husband, who's a real computer guy, like he says I'm kind of wrong, but the way I kind of think of it is here in Janesville, you have your login, right? If you use that login at Parker High School, is it going to work? Yeah. Yeah, it does. If you go down to Roosevelt Elementary School, is it going to work? Yeah. What about Marshall Middle School? Yeah. What about Madison Memorial?
Yeah.
No, it's not going to work up in Madison, is it? Because they're not part of our school district. They're not part of our intranet. So our intranet is within our group. Our group is the Janesville School District. You go outside of that. You go over to Edgerton High School. It's not going to work. Okay? But you are able to get a hold of other computers. But you can't use our intranet. You have to use the internet. So this goes between bigger things. Just like it, we actually have intra-state highways, like Highway 26. Highway 26 starts in Janesville. It goes up somewhere, ends in Green Bay-ish area. Maybe even further than that, I guess. I don't know for sure. I think it goes close to that far, at least up to Appleton. I know it'll get you to, what's the one south of Appleton? Oshkosh. I know it'll get you to Oshkosh. All right. So that goes within the state. We also have interstates. So that'll take us from Wisconsin. That's my sad looking Wisconsin, you guys. We've got Illinois down here. We have Minnesota over here. Okay. Wisconsin kind of carves out. We've got an Interstate 90 that goes all the way over to Washington State, and it goes all the way over to the East Coast over here somewhere. I don't know where it ends up over there. Massachusetts, maybe. Okay. But that goes between states. That's an interstate. Okay. So when we look at these forces, when we're talking about in terms of atoms, and molecules, we have intramolecular forces. Those are bonds between atoms. We've already studied a couple of those. Ionic and covalent are two that we've studied. And typically, that is what we call these. We don't call them intramolecular forces. We just call them by what they are, either ionic or covalent. These are within atoms. So if I were to draw a water molecule, my water molecule would look something like this. These here, my intramolecular forces, these would be, oh, it won't work there, will it? Okay, maybe not. All good plans of mice and men. It doesn't work for that. Okay, these are intramolecular forces here. Notice that I've drawn them with a solid line indicating strength. Okay, because they are stronger than intermolecular forces. Intermolecular forces are going to be forces between molecules. I don't know why that box is there. There, make it go away. So here I've got another water molecule. Okay, and I've got intermolecular forces between there. So I'm going to draw those with a dashed line. That dashed line shows that they're weaker forces. They're not as strong. Because if you think about like Coulomb's law, remember we talked about Coulomb? What were the two parts of Coulomb's law that factored in strength? The amount of force, and what was the other part? How far away it is. Yeah, how far away it is. So these bonds are much closer to these atoms than the molecules are one to another. And so that's why this force of attraction is less. So this is going to be weaker. All right. There are three primary ones that we're going to talk about, which are our dispersion forces, our dipole-dipole, and our hydrogen bonds. And we'll talk about, we're not going to get to these two today. We'll get to some of dispersion today. All right. Good? All right. Don't write this down. You already know about ionic bonds. You know that ionic bonds have the positive and negative charges around them. Okay. When they do that, they form that crystal lattice structure. So that causes them to be really strong. And at normal room temperatures, that's what gives them the fact that they are going to be a solid. So they're solid under normal conditions. So ionic compounds are solids. So we're not going to talk about them because we're not going to be able to look and see much difference in them. There's not much variation. They're always just going to be solids. We don't have enough heat here in my lab to melt them. Okay. So yay, they're boring. We move on. Okay. We are going to turn our attention then to covalent compounds. So these covalent compounds have low melting and boiling points because they have weak intermolecular forces. So that's what we're going to look at. Covalent compounds have weak intermolecular forces, which gives them low melting and boiling points. Do you need to write down every word on this slide? No. Summarize it. All right, you good? Anybody still writing? You need more time? Good. All right. Intermolecular forces of attraction, they are going to be between the molecules, which we've already said, and these are the 4 types. All right, you good? Anybody need more time? These 3 are called van der Waals forces. Now, you're probably getting sick of writing all of this down. So let me give you some abbreviations that are accepted anywhere. Okay? You go on and take AP with me. You can use these on the AP exam. You go off to college somewhere. You can use these at college. Okay? Any chemistry professor worth anything is going to know what these are. This is a very common abbreviation. We abbreviate these IMF. So we call these IMFs. We abbreviate these LDF, or London Dispersion Forces. So you don't have to write all of this out. You can use these abbreviations. They're accepted anywhere. It's kind of like your Visa card. They accept it anywhere. Just kidding. Except Woodman's. Not going to happen. All right. But remember, all of these are always going to be weaker than your covalent bonds. Okay? All right. Intermolecular forces are going to determine. So these determine. So IMFs govern. If you would rather determine whatever works for you so that you can remember what it is, when something is a solid, liquid, or gas. This is why something is a solid, liquid, or gas at room temperature, which I think is kind of cool. Like, why is your desk a solid and water is liquid? Like, they're all the same temperature. So why's one a solid and one's a liquid, and then you got gas out here? Like, what's the deal with that? It all comes down to these IMFs. And you have these cohesive forces. So cohesive means to do what? Hold together, yeah. So you've got these cohesive forces, which are your IMFs, and you have a disruptive force. Disruptive force, typically thermal energy. What's a 4-letter word that I could use to replace that with? Heat. Okay? So this is typically heat. So I don't have to write all of that out. I can just write out the word heat. You guys need to find a shorter way to do some of your notes so that you're not taking I don't mind you taking time. Don't get me wrong. But I'm trying to teach you how to simplify your life a little bit. Okay? All right. So I believe, let me see. No, it won't let me move it down at all. I have solid written down here on your paper. I have liquid written down, and I have gas. And I believe it's in this order, yes?
Yeah.
All right. We are going to look at the connection between these. When you have a solid, you have very strong cohesive forces compared to the disruptive forces of heat. So your desk, your pencil, okay, those are all things that are going to have very strong IMFs compared to room temperature. You take some of those things, take your pencil, okay, it's made out of plastic. You put that in the oven for a few minutes, what's going to happen to it? It's going to melt because it's going to have done what to the cohesive forces? It's going to have reduced them. There's still going to be some there, okay? That's why it's a liquid. You keep going and get rid of all of them, and guess what you got? A gas. So this is going to have stronger cohesive than disruptive. When you get to a gas, that flips. And your cohesive, your IMFs are gone for the most part. And that disruptive overwhelms them. So here, sitting in this room, you've got gas all around you. You can't see it, thankfully, because we don't want the gases that we can see usually. Those are bad gases. Now, you can see a gas, you don't want it around you, okay? So gases are all around you. They have very weak IMFs. Your solids have very strong ones. Those strong IMFs lock those molecules into position and keep them from moving or sliding past one another. You weaken those IMFs, and that's going to allow those particles to slide past one another. And that's why you have a liquid at that point. But you still have volume there. It's still going to have its own volume, and you can measure that. Okay? But they're going to be able to slide past one another. That is the definition of a fluid. It's able to flow. You weaken those even more, and then they're going to go free. There's no IMFs controlling them. And so it spreads out as far and wide as the container that it's in allows it to. And that's the difference between a solid, liquid, and gas. It's still the same molecule. So if we're talking about water, for example, okay, here's your water molecule. When you have a solid, you're going to have that force of attraction between those be very, 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 very strong. Okay? So there's a force of attraction there. You start removing some of that heat, and what's going to happen to that attraction? It lessens, and these particles are able to slide past one another, but they still have a volume. You remove all of those all together, and now they're free to spread out. So this is your gas vapor at that point. Yep, when you freeze a liquid, you are increasing the IMFs. You're pulling that heat energy out. That's what your freezer's doing, okay? So it's pulling that heat energy out. Or at night when the temperature drops, okay? Temperature drops, that heat energy is being pulled out, and it's reestablishing those IMFs. So here's reestablished as a liquid, and now it's reestablished them as a solid. And that's the difference. But you're still dealing with water molecules. You're still dealing with H2O here. So you have not gone through a chemical change. And that is why phase changes are physical changes, because all you're doing is altering these IMFs. You're not altering the chemical structure of that material. It is still water in this case, or whatever it is that you're freezing. But that's the difference between a solid, liquid, and gas, is just the IMFs. All right, so I already said all that. All right, so London dispersion forces are going to be temporary dipoles. So let's dissect that word. What does di mean? Two. So we are going to have two poles here. And these poles are going to be a negative pole and a positive pole. But they're temporary, which means that they're not going to happen. They don't stay there long. Okay? So, every atom, everything has electrons, yes? Okay? Those electrons are constantly moving around in here. They're moving. Every once in a while, you get a shift of the electron. You end up with more on one side than you do on another. If you have more electrons over here, that side is going to be negative. This side will then be positive. Another molecule comes along, and guess what? It's going to cause the electrons from that to shift over here and get attracted to this positive end. If some of those shift over here, that leaves this side positive. And it's like a chain reaction. These are called induced dipoles because they don't happen like all the time. This caused it to happen. This is an instantaneous one because those electrons got disturbed, and this was induced by that. This only happens for a split second, like super short amount of time, but it happens. Okay. Now, since everything has electrons, and those electrons are always moving because we're not at 0 Kelvin, which is absolute zero, right? Since that's always moving, and this happens all the time, then that means that London dispersion forces happen in all substances. It does not matter what substance it is, LDF exists there. So it is in all substances. When they ask you to list the IMFs in a particular substance, without even thinking, your hand should go down and write down 3 lovely letters, which are in that order. Yes, LDF in that order, because everything has it. So don't even think about it. Just sit down, write LDF. Then you can think about the other ones that I'm going to talk to you about tomorrow. But it should be an automatic gut reaction that you would just go ahead and write that down. You don't even have to think about it. All right. I want you to visualize me walking across the floor with a glass of water that's filled almost to the very tippy top with water. If I'm careful, do you think that I could walk from my desk all the way to the back of the room without spilling anything? If I'm careful. Yeah, that's doable. Now, let's take a very large tub of water. Let's imagine that I'm strong and I can carry said tub of water. It is filled almost to the very brim with water. Do you think that if I am very careful, I would be able to walk to the back of the room with that without spilling anything? I'm klutzy. Just remember. Would you be able to do that?
No.
Okay, there we go. I wouldn't either. Okay. Because there's so much more water in here and it's going to get sloshy. I mean, you can imagine the sloshy side to side action that's going to happen with that. This is doable. This isn't. Okay. It's the same idea with these electrons. As you're walking, or as you're not walking, but as you increase the number of electrons, you have more electrons to shift going back and forth here. So the more electrons you have to shift, the stronger your LDF is going to be. Does that make sense? Okay. So this is going to increase with the number of electrons. Good? All right. So as the number of electrons increases, your LD, London dispersion, I forgot my D here, forces become stronger. That's not an eraser. So my London dispersion forces are going to become greater as my number of electrons increases. My boiling point is also going to increase. What else will increase? Melting point. Yes, very good. All of those things will increase. So as my number of electrons increases, my LDF increases, my boiling point increases, and my melting point will also increase. Now, let's talk melting point here. What is the melting point of water? What temperature? You're driving. Come on. You should know this. If you're driving now, it's important to know what temperature water freezes at if you're going to be driving, so you know the road conditions out there. Okay, I'll take Fahrenheit if you want to give me Fahrenheit. It's also 0 degrees Celsius for those of you playing along in the metric system. Okay, that is the melting point of water. What is the freezing point of water?
Wait, that's a freezing point.
It is, yes.
Is this the melting point?
Yes, melting point and freezing point are the same temperature. Did I just blow your mind?
It's only for water now.
It's for everything. Everything, the melting point and the freezing point are the exact same temperature. So let's talk about what the difference between that is. Let me go back up to here. The difference is, are you adding this disruptive force in, stovetop, for example? Okay, if I have a piece of ice there, is it going to, it's going to melt if I put it on the stovetop, right? Heat it up. Or if I just bring it out in room temperature, it's going to melt. Okay, because these disruptive forces are going to be greater than its cohesive force. If, however, I take that same thing and I put it in the freezer, what am I going to be doing? I'm removing the heat. So at that point, the determination of whether it's a freezing point or a melting point is whether we're adding heat in or removing heat. But it's going to happen at the same temperature.
It's like, if it's like negative 10 Celsius and it's already frozen, then it goes back to 0, then it'll start to melt.
Yep, it'll eventually go to, if you have it on the stovetop, yeah. And we're actually going to do that lab after spring break, where I actually make you melt ice. Yeah, you have to melt ice and then boil it for 5 minutes. I know. But it gets the point across. But yeah, it's 0 degrees Celsius. It is going to melt. If you're adding heat in, if you're pulling heat out, it's going to freeze. And that's the difference, is what's happening with that disruptive force. Is it going to be removed and your IMFs increase? So that is the break point. The break point right here is that melting or freezing point, depending on what's happening with this. Kind of cool, huh?
Is that also the same for like the transition between liquid and gas?
Well, that's a little different because that has to do somewhat with the surface tension, okay, which is what you were looking at in terms of your penny, okay, was the surface tension. As you increase the IMFs, you're increasing that surface tension. And you can have it change from liquid to gas in 2 ways, right? There's 2 ways to go through this process. One of them is very rapid, which is how? No, we're going from liquid to gas. Boiling is very rapid, but there's another way. Why did I tell you to cap those test tubes? Evaporating. Right. That's a very slow process. Okay. So that's a little trickier. That has to do with some of that surface tension and where that transition is happening. If you are boiling something, okay, have you ever watched something boil? Where do the gas bubbles form? At the bottom, and then they raise up because they're less dense, and then they pop at the top. Okay? When you go through evaporation, that happens right at the very surface. And that has to do with them kind of transitioning from that. And it's getting heat or energy from the room a little bit, but it's happening very slowly. Okay? So that's a little trickier. But yeah. All right. So I am leaving off here. Where was I at for you guys? Hold on. Okay. Write down that I was at slide 27. So I know where to start up again tomorrow. Okay. All right. So tonight you're going to go home and finish your lab. Okay.